Induction heating can be used in different industrial applications by providing a highly efficient and controlled way to heat metals and non-metal parts when considering heating methods. The most basic and widely known is open flame heating in this process. A flame heats the part and filler metal is added to the joint, but less than half of the heat is absorbed by the metal, while the rest is wasted in the environment. To compensate, multiple flames are sometimes used, but this method lacks precision and repeatability, making it unsuitable for high-volume manufacturing. Another method is using ovens or furnaces which contain heat within a closed box, ensuring any part placed inside reaches the set temperature. However, ovens heat the entire part even when only a small section needs heating, and they require long startup times, making them costly to operate, especially when running continuously between production cycles. Resistance heating is one of the most efficient methods as it converts nearly all electrical energy into heat, but it requires direct contact with the part using electrodes, which can be impractical in high-volume production. Due to repeatability and safety concerns, it is best suited for applications where large metal pieces are heated for extended durations. Laser heating is an emerging technology capable of applying intense heat to very small areas, making it ideal for precise applications like metal cutting. But due to high cost per kilowatt, it is not widely used for general heating in industrial processes. In many applications, heating only a specific surface area is necessary to modify mechanical properties or accelerate manufacturing processes. This is where induction heating excels its ability to selectively heat small portions of a part without affecting surrounding areas, makes it highly efficient, resulting in faster heating and cooling cycles, reducing overall production time and energy costs. Unlike other methods, induction does not require direct contact with the part, eliminating contamination risks and wear on heating elements, making it an essential tool for modern manufacturing. Understanding induction, heating coils and processes. Induction coils can form tunnels for parts to pass through, ideal for high-speed production. Operating frequency. Lower frequencies heat deeper, higher frequencies heat shallower. Thermocouples. K-type thermocouples monitor temperatures up to 2,000 degrees Fahrenheit, properly attached for accuracy. Frequency considerations. Induction power supplies operate within a set range. Exceeding the threshold has minimal effect, but going below reduces efficiency. Clamping electrodes. Efficient for heating metal rods, requiring proper insulation for safety. Heating ramp rate. Copper handles higher power density, while steel requires controlled ramping. Heating concealed parts. Induction provides precise heating where external methods fail. System calibration. Digital induction systems don't require calibration. Helical versus pancake coils. Helical coils are more efficient. Pancake coils need more time or power. Coil design. More turns of thinner tubing improve efficiency, limited by voltage, cooling, and water flow. Cooling systems. Use distilled water to prevent buildup. Avoid deionized water to prevent metal corrosion. Alternatives to thermocouples. Fiber optic sensors work where thermocouples are impractical. Heat gradient. The highest heat gradient should be inside the coil, influenced by coil shape, spacing, material, and part geometry. Coil calibration. Inductance meters, not electrical resistance, ensure coil consistency. Mastering these factors optimizes efficiency, safety, and performance in induction heating.